Petr Dunin-Barkovskii. Petr, prepare your screen.
Yep.
Petr, how to put it, is not exactly a young scientist. Well, at least not young probably anymore. So probably you feel pity about that, but it's very last time you are in the young session.
Well, yeah. So
And Petr, he's in Moscow, so in Higher School of Economics and Skoltech, and he will tell us about explicit closed algebraic formulas for hypergeometric KP, generalized Hurwitz, endpoint functions. So about all this stuff, please.
Okay, thank you. So do you hear me well? So first of all,
yes.
And do you see my pointer?
Yes.
Okay, thank you. So first of all, I would like to thank the organizers for organizing this wonderful workshop and for the opportunity to speak here. It has been a real pleasure to participate in this workshop over the years. I think my first time was back in 2010 when we had this workshop was held for the second time. Now it's seventh time. So yeah, it has been a real pleasure. So now what I'm going to talk about is joint work with Boris Bычков, Maxim Kazaryan, and Sergei Shadrin. So you can find it on arXiv. And it's, well, as you can see, explicit closed algebraic formulas for basically generalized Hurwitz endpoint functions. So what is that? Well, okay, let's proceed. So first, let's outline the plan. First of all, I will introduce these KP tau functions of hypergeometric type, which are also known as Orlov-Shcherbin tau functions, and how they are related to general formal weighted Hurwitz numbers, and which known and studied types of Hurwitz numbers are encompassed here in this general picture. Then I will make a rationality statement, which is our theorem in our paper regarding the endpoint functions of these Hurwitz numbers. I will provide explicit examples of this of how this formula works, and then I will give a general formula which works in all situations, and I will briefly discuss applications. And actually, after my talk, there will be a talk by Boris Bычкov, so Bori will discuss how our explicit formula, how it allows to obtain topological recursion for almost complete generality here. Right. So who are these KP tau functions of hypergeometric type? Basically, consider the following formal power series. So this whole actually will work in the domain of formal power series. So this is quite a general situation. So consider two formal power series, which we call psi of y and y of z. It's a little unfortunate that, I mean, it might be confusing for somebody that this argument here is y and the second function is y of z. Actually, the reason for this notation is that we will actually we will plug this y into psi, and it will be used like that. So it's quite natural to call this formal variable in the formal power series psi as y, and the formal power series and the formal variable in the formal power series y we call z here. Then after we fix these formal power series, so ck and sk are collections of just numbers, and then we can consider the following thing. Here, the sum goes over all Young diagrams lambda, including the empty one. And here, the S lambda of P is the sure function, which is a polynomial in the power sum variables pk. For a given lambda, it's a polynomial of homogeneous degree size of lambda. And here you can see that, so actually what will this Z depend on? It will depend on formal infinite number of formal formal variables pk. Also, it will depend on formal variable h bar. So how does it depend on our power series psi and y? So psi plays a role here. We plug h bar times g minus I here. So g minus I is the content, what's called the content of the box, the ijth box in the Young diagram lambda, and we plug it into psi. This is formal series psi. And y plays a role here in terms of its coefficients sk. So basically, you have the sk entering here, the sure function, which the second sure function which you have here. SKs are entering here, and when we consider a sum like that, it turns out that this is a tau function of the KP hierarchy, or of HKP, and it's what's called a KP tau function of hypergeometric type. So they have been studied since quite long ago. So for instance, functions like that were mentioned in this work, and then they were specifically studied by Orlov and Sherbin in several papers. So for instance, this one. So these functions are also known as Orlov-Sherbin tau functions. Now, if you take the logarithm of this tau function, which we call f, then you can consider its what we call genus expansion. The expansion, we can consider its coefficients in front of the p monomials and expand it as in terms of the formal variable h bar. And the coefficients here are some numbers which are labeled by G and labeled by Young diagram mu. So these are coefficients in front of monomials and p variables in this f in front of some specific power of h bar. And this is what we call this hg mu. This is what we call a general formal weighted double Hurwitz number. So this is firmly in this formal power series domain. So if you have any formal power series psi and y, then you can get these numbers h. It's not completely obvious why they are well defined, why this in particular, why this genus expansion works, why you only have finite sums here, but it actually follows from our theorem that they are indeed well defined in the more general formal power series situation. So why do we call these numbers general formal weighted double Hurwitz numbers? Well, because they actually, for some specific psi and y, they encompass known situations of double Hurwitz numbers and more specific situations. So for instance, you can see a table here. If psi of y is just equal to y and y of z is just equal to z, what you get is just the usual simple Hurwitz numbers. Then, for instance, if you place psi of y being a logarithm of 1 over 1 over y, 1 minus y, and y equals to z to the power q, then you get what's called q orbifold monotone Hurwitz numbers. Also, you can see from this table, so you can get Buscema-Liouville numbers, for instance, by taking this and for your psi. You can consider general, for instance, polynomial weighted double Hurwitz numbers when you terminate the formal power series and take just a polynomial for x of psi and for y of z. This is, for instance, the situation which was considered by Alexander of Chapuis, Einar, and Hernad in their paper. I will refer to that paper a little bit later as well. So, but also you can consider the most general situation when you just have some formal power series. Also, we can consider what we call the H-deformed case. So basically, on the previous slide, I said that the coefficients of our psi and y, they were just numbers, but you can consider them as formal power series in H bar, or more specifically in H bar squared. And this allows us to include, and actually our theory, so what I will say later, so our main theorem and so on, so it will work for the H-deformed case, H-bar deformed case similarly well. And this allows us to encompass the some further cases, namely R-spin Hurwitz numbers, and for instance, also the extended Gurevaffa partition function of colored half-loop polynomials of torus knots. So here you see what you have to put for psi and y, psi of y and y of z in order to get these cases. Basically, so what? Basically, every type of Hurwitz numbers and of Hurwitz numbers so far studied in relation to topological recursion, it can be included here. Now, so what will our statement be related to? So the statement will be related to the endpoint functions. So who are the endpoint functions? Basically, they are functions defined like this. You introduce formal variables, which we call capital X here, and so basically they can be thought of, once you consider the genus expansion, they can be thought of just as generating functions of those numbers, which I called general formal weighted Hurwitz numbers. So this, again, you can think about it just in terms of formal power series. So these are some formal power series in these formal variables capital X. And our statement will be about these functions. In particular, so the statement is that, in fact, these functions, they become rational functions of some small number of building blocks. So let's see what we say. So in order, what I mean when I say that they become rational, so they become rational after a certain change of variables. So this change of variables was used by Alexandrov, Chapuis, and Hernad in their papers, where they basically studied polynomial weighted Hurwitz numbers and proved topological recursion for that case. So this is the change of variables. So you can think about this again as just some formal power series in our situation. So this is the change of variables. So we pass from the formal variables x, which we had here on the previous slide, we pass to the variable z. So this, in terms of topological recursion, this will be the variable on the spectral curve. But actually our statement, so our formula for the endpoint functions, it holds in actually in more general situation when we have topological recursion. So in the situation of formal power series. So we use this change of variables, and then we obtain an explicit formula for endpoint functions, written as functions in z variables, and it's an explicit formula. It'll be a rational expression in terms of small number of building blocks. And in a moment, I will explain how this will look. So this is the theorem. Basically, we say that, so here, the general situation is when G and N are not equal to 0, 1 or 0, 2, but for 0, 1 and 0, 2, we also can give explicit formulas. Just for brevity, I am not writing them here. So the theorem is that these endpoint functions, after you apply the change of variables, this HSE change of variables, which I mentioned on the previous slide, so you get a formula like this, which is actually for a given G and N, it becomes a finite sum. So this will be a finite sum where the P, J1 and so on, Jn are polynomials, are finite polynomials in these building blocks. Building blocks are just these rational functions of z variables, and then the derivatives of our psi, which was a formal power series, and the derivatives of our y. And also we have this q playing a role here, and we take derivatives like that of the whole thing. So like I said, for a given G and N, this becomes a finite rational expression in terms of all these guys. And here I'm just
whether qi is q depending on zi.
Yeah, thank you for this question. Yes, precisely. So qi is q of zi. Yes. qi is precisely q of zi, and di is d of zi. Yes, thank you. So this is, like I said, so this is the general form of this rationality statement, so that this is the statement that we get finite rational expression of in terms of these guys. But this is actually what we do get is more than that. So we not only prove that they are finite rational expressions, but we also give explicit formulas for this HGN in terms of sums over graphs. But let's study first this form. You see that, for instance, if y and psi, like I said, so this general statement, it works in the domain of formal power series. It's completely general. Then what can you say if your y and psi, or more precisely y prime and psi prime, if they are rational functions? And this is actually the case in most of the examples in the table, which I've shown several slides before. So, for instance, for BMS numbers, for the simple Hurwitz numbers, for monotone, and so on. So for R spin, so in most of those situations, these are rational functions. And then actually, this theorem implies that HGN also becomes a rational function in variables z1 and so on zn, which I mean, in the cases when there is we have already topological recursion, we know this, right? For the cases where we know that there is topological recursion for some sort of those numbers, then topological recursion implies that these endpoint functions are rational functions on the spectral curve in most cases. So let me show you some examples of how those general formulas look like. So this is completely general. I have not specified psi and y. again, you can think of them as formal power series. So we have, so here, these formulas were actually computed on, Maxim Kazaryan has this Mathematica program where this formula, our explicit formula, can be is realized, where for a given GNN, this program can obtain explicit answers of this sort, where we have not, like I said, so here we haven't specified anything about psi and y. They are just formal power series. You see that the expressions are not very, I mean, they start to be quite large when GNN are grow, but this is all very explicit. So this, again, let me stress that this can be for any reasonable GNN. You can plug GNN into the computer and get a formula like that, which holds for without any assumptions on psi and y, further that they are just some formal power series. So for instance, if you consider some specific case out of the table, which I mentioned there, then you can plug your psi and y and get some very explicit formulas. Here is the notation, but let me proceed. So let me give the general formula. So actually, our general formula, like I said, it works in even more generality, in even greater generality, namely for this case when psi and y are also depending on h bar. So when they are formal power series of this sort, where the coefficients ckm and skm are just numbers and h bar enters the picture. So we call them psi hat and y hat here, and psi and y are you get when plugging h to be 0. And the general formula, it looks like this. So I've given here our general formula for what we call wgen, which are the hn, where you apply where you differentiate once with respect to every variable. Basically, this wgen is what's of interest to topological recursion, because this is basically the wgen functions. They are basically what you get if you take the endpoint differentials of the topological recursion and just divide by dx1 and so on dxn. So then you get these wgen functions, and here is our general formula. But we also have a formula for h themselves. I have not given it here because it's larger, but we also have an explicit formula for h as well. It's a little bit more, it's a little bit uglier because basically you have to integrate this formula, and there are some special cases which arise there, but it can be done, and it is done in our paper. So let me explain how this general formula works. So this is a formula written in terms of sum over graphs. You have sum over all connected simple graphs on n labeled vertices, and on each edge you put an expression like this, where curly s is just this guy. So you put an expression like this on every edge, and at each vertex you have an operator like this. So it's a little bit complicated looking, but it's very explicit and can be computed in any given situation. So you can see that here you have some infinite sums, but this is these infinite sums are kind of deceiving in terms of, namely, for if you fix GNN, so fix this power of h bar, which you're interested in, and fix n, then out of this general infinite expression, only a finite number of terms survives. So everything is finite for fixed GNN. This this formula is completely finite and explicit. And like I said, it works in the domain of, in the full generality in the domain of formal power series with some, well, I mean, then you of course, you can ask what is this rational function, how you can think of this in terms of formal power series. Well, there are some subtleties, but it's very general in any case. So you think of this guy basically as its expansion for if k is less than L, then you consider zk to be less than zl and expand this guy in the series, and everything then becomes just a formal power series. So this is our general formula. But then why is it interesting? So first of all, this is a finite rational, it gives finite rational expressions in full generality, but also it has applications. So one application is topological recursion. So basically, using this general formula, you can prove topological recursion uniformly for all those examples of Hurwitz numbers which are listed in the table, which I have given several in the beginning of my talk. We had a number of papers where groups of people proved the topological recursion for all those numbers using some complicated techniques special for each case. But our approach, it gives a uniform and in a sense straightforward, but I mean, this will be in Boris' talk. So a uniform proof of topological recursion for all these previously studied examples of Hurwitz numbers, which are known in the literature, and in fact, in quite a bit more generality. So of course, I mean, we had also, there was a work by, which I mentioned, by Alexandrov, and Aaron Harnad, which proved for many of the known cases, but not for all of them, because they had the basically polynomial instead of, they had what we here called polynomial psi and y, and they had actually in their proof some further restrictions. So our approach, it works in basically, you can't say that you have topological recursion for any formal power series. No, you need to introduce some assumptions. But so in the next talk, Borja will explain this. Also, there is this conjecture due to Gaetan and Alba, which I think Alba mentioned in her talk the day before yesterday, I think. The conjecture that the topological recursion holds for fully simple maps, and this conjecture can be proved by our technique. Namely, we can obtain a formula very similar to this one for fully simple maps, just that you will have endpoint functions of ordinary maps entering there. But then this formula allows us to prove topological recursion for fully simple maps, and to prove, which means to prove the conjecture due to Gaetan and Alba. And so this actually, we are finishing writing this down, and it will soon appear on arXiv. And also you can use this in order to have applications for ELSV type formulas, like the ones which Danila mentioned in his talk. So basically, for most of the cases which Danila mentioned in his talk, you can apply our formula, get the topological recursion, then apply this DOS correspondence, and get some ELSV type formula. But of course, you need to study what happens on the cohomological field theory side in order to explicitly get the right-hand side. But still, you get a uniform proof of ELSV type formulas in this way. And so I mean, there are probably, or actually, it seems that there are more applications of this approach, but we're still working on that. So yeah, I think thanks.
Thank you, Petya. Some questions?
So could you elaborate perhaps a bit on why Gaetan and Alba's conjecture does not fit in this scheme immediately? Like, what do you need to change?
Well, I mean, immediately it doesn't fit because it cannot be the maps and fully simple maps. They cannot be represented in terms of just this capital function of hypergeometric type. So it's, if you talk about them, and I haven't written here the formulas in terms of correlators, but they are a little bit different for the maps cases. So basically, you get what's called T deformation there. So you get something what we call T deformed capital functions of hypergeometric type. So immediately this T deformation, it does not fit into this picture. And actually, we cannot at the moment prove a formula like this for instance, just for maps, or for fully simple maps themselves from scratch, just starting the correlator. We cannot at the moment prove it. But if you have topological recursion for maps, which is known to exist, right? Then it implies that basically there is a duality. So for topological recursion for maps implies that we can write a formula like this, which relates here endpoint functions of fully simple maps to the endpoint functions of maps on the right hand side. Basically, here on the edges, instead of these guys, you will have WGNs of maps.
Right.
You will get the WGNs of fully simple maps. And then if you have topological recursion for maps, then this approach allows you to prove from that topological recursion for fully simple maps. But actually, this duality holds in more generality, not only for maps and fully simple maps. It's the duality statement is quite a bit more general. But yeah, topological recursion we have only managed for now to prove for fully simple maps, where the because only for maps it is known out of the problems. But yeah.
Okay.
Okay, thanks.
Can I ask a question?
Yeah.
Yes, Elma.
So do you get then some functional relations between the generating series of ordinary maps and fully simple maps?
Yeah, precisely. Yes,
duality?
precisely. We get a relation like this. So that's basically we get a functional relation. So on the left, you get the endpoint function for fully simple maps, and on the right, you get a formula like this with a very similar operator U here, and in place of WKL, you get here here in the exponential, you get, instead of these guys, you get WGNs of maps. Here the sum is over graphs, and for maps, in this formula which I'm talking about, it will be over multi-graphs. So instead of edges, you'll get this multi-edges with multiple number of endpoints, and then here you will have the WGN and the exponential, basically.
Okay, nice. Well, I would like to hear the details of that.
So it will soon be on archive, but yeah.
Yes, but we'll have also next talk, Boris talk. So
Boris talk, actually, Boris talk, so he will still talk about the topological recursion for these guys, and not for the fully simple maps, because I mean we're still writing that down, but hopefully soon it will appear on archive.
So let's continue.
Okay, thank you.
Thank you. So thank you again.